Good morning, everyone. Thank you so much for joining us today. My name is Victoria, and I'm a Senior Marketing Coordinator at 2H Offshore. I want to welcome you all to our webinar today entitled Exploring Fatigue Monitoring and Life Extension for Top Tension Production Riser Systems. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Bulent Mirjan. Bulent is a principal engineer at 2H's Houston office. He has more than 10 years of engineering experience in structural analysis, subsea design, integrity management, and structural monitoring. Bulent received his PhD in civil engineering from the University of Minnesota. He's a professional engineer licensed in Texas, and he's also a part-time senior lecturer at the University of Houston, teaching structural analysis and design courses. So with that, I'm going to pass things over to Bulent.
Thank you, Victoria. Hello, everyone. Hope everybody's doing well. So here is our outline for this webinar today. I would like to begin with a brief introduction. Let me get my laser here. I'm going to start with a brief introduction, and then I will describe a case study and talk about the riser and monitoring systems considered. And then I will talk about key findings from the field data screening, and more importantly, the impact of top tension variation on the riser response. And next, I will show the fatigue results calculated based on monitoring data. And finally, I will present conclusions and recommendations. Yeah, so top tension riser systems have been widely used in the deepwater oil and gas fields, and many TTRs were installed worldwide more than 20 years ago, and now some of these risers are reaching to their design lives. Operators must decide whether to continue using the risers or decommission them, and the operators generally prefer to continue, and as in many cases these wells are still productive beyond their original or design lives. However, this requires detailed life extension and fitness for service assessments, and in some cases these may require costly out-of-service inspections. So what are the potential solutions for TTR life extension? And one will be to conduct a risk-based assessment. This has been discussed in detail in another 2H webinar. You can refer to this webinar if you are interested and if you want to get more information on this. So this is a risk-based assessment of the TTR life extension. And another option will be to deploy a fatigue monitoring system to assure the long-term integrity of the TTR. So that's what we are going to discuss in this webinar. And so the main objectives of this webinar are to discuss the value of TTR field measurements and data analytics, and to show the impact of top tension on TTR fatigue response using monitoring data. So TTRs provide production conduits from the seabed to facility, the topside facility, and permit workover operations on the wells. And you can see a schematic of a TTR here. So in this presentation, I'm going to talk about the case study. And in this case study, there are top tension riser systems deployed from a spar operating in a water depth of approximately 5,000 feet. And this spar consists of 6 top tension risers, and 2 of these TTRs are instrumented for this work. And each TTR is a dual casing system consisting of a 12 3/4 inch outer casing and 9 5/8 inch inner casing. And each riser is tensioned using upthrust provided by the buoyancy can and stem system at the top. So we monitored two risers, TTR1 and TTR2, simultaneously for varying top tension settings, and 6 motion sensors are installed on each TTR as shown in this figure. One sensor is installed at the top of the riser below the stem pipe, and three loggers or sensors are above the stress joint, spaced at 150 feet, and one sensor at the bottom of the lower stress joint, and there's another sensor on the wellhead. The ROE depths for all sensors installed on the risers are given in this table. 2 monitoring campaigns are conducted for a total period of 18 days. The first campaign lasts 2 days, and the second campaign lasted 16 days. And at the end of the monitoring campaign, sensor data is downloaded and sent to onshore for analysis. During the monitoring campaigns, the risers are filled with treated seawater, and the top tension of each riser is controlled by the flooding, the air can chambers, and measured using load cells at the top. And TTR1 top tension is increased from 440 kips to 835 kips. 35 kips during the monitoring campaign, and at the same time for TTR2 top tension is increased from 545 kips to 675 kips. So here you see subsea images for some of the installed sensors. So standalone battery operated sensors are used. They are designed to be installed and retrieved by ROV using a magnetic holder. And magnetic holders are field proven and allow for ease of installation. You can see it over here. This black component is the magnetic holder, and this is the casing for the sensors. And each sensor records data continuously with logging frequency of 10 Hertz. And actually 10 Hertz logging frequency is sufficient to capture riser wave and VIV response in the field, and that's what we typically use. And these sensors measure 3D accelerations and 2D angular rates. So it's always good practice to review raw data and confirm the quality before performing any advanced data analytics. So we perform sensor validation, such as sensor noise check and resolution check, and compare them with the sensor specification and make sure that they work as expected. And afterwards, we conducted statistical analysis and calculated the RMS, root mean square accelerations, for all sensors. Next, we correlated the accelerations with measured wave heights and measured current speeds, and we also correlated with the say top tension operational input, and then perform spectral analysis. What I mean is the fast Fourier transformation for each event, and then identify VIV and wave dominant events. So here, as I said, the data is recorded continuously. So for analysis, of course, they are converted into data packages in the form of, say, 30 minutes, and we call them as events. So one event, or an event, means a time trace including 30 minutes long data. Okay, so Here we look at some statistics. So we calculated the root mean square accelerations and plotted through the monitoring campaign for all sensors. TTR1 data is shown on the left and TTR2 data is shown on the right. So when we look at this data, we see that both risers, TTR1 and TTR2, show comparable motions below the stem pipe, which is represented by this brown color here. And this is something we expect, right? Because these TTRs are attached to this spar, and and this senses right below the stem, so they are directly transferring the spar motions to the riser. So they are comparable here as I expected. And then for both risers, accelerations near the bottom are always higher than the stem pipe, right? So for this, what I mean is this blue, orange, and green lines, they are showing the acceleration RMS values coming from the sensors above the stress joint, and they are greater than the motions observed at the stem pipe. And when we look at the wellhead and bottom stress joint accelerations, they are blue and red colors here. Actually, we are seeing almost a flat line. It's actually, these motions are so small that they are below the sensor noise level. And so this confirms that the wellhead motions are negligible during this monitoring campaign for both risers. So here in these figures, we focus on data from the sensors at 150 feet above the stress joint. So we are just looking at one sensor right now. But we compare these accelerations with the environmental measurements, such as wave height, measured wave height, and current speed. So the TTR1 accelerations in this figure is shown in red color, and TTR2 accelerations are shown in blue color. The figure on the left here correlates these motions with the measured wave height, and the figure on the right shows the correlation of these accelerations with the measured current speed. So during the monitoring campaign, a maximum significant wave height is around 11 feet, and the maximum current speed is around 1.3 knots here. So when we look at here, these two figures, in general, TTR1 and TTR2 motions are in good agreement with the measured wave height. So this indicates that the measured riser motions are actually, the measured riser response is mostly dominated by the wave-induced effects. So here you see a couple of examples for spectral response. We use this spectral results to identify the riser response. Mostly, is it dominated by the wave motions or VIV, vortex-induced vibrations? So here you see one selected example. So this is a good example for a riser VIV response. You can see that a narrow banded response is observed in all sensors. So you see all sensors over here. This is the spectral amplitude and this is the frequency. And you see that narrow banded response is observed in all sensors at the same frequency. So this is a good example for VIV response. And on the other hand, when we look here, by the way, yes, we observed this VIV during this monitoring campaign, but the thing is, it's not really dominating the riser motions. So we just observe few events like that. So it's not very critical for the for this riser system. And the spectra plot on the right here is a good example for first and second order motions. The first order motions or wave frequency response is typically occur within the frequency range from say 0.025 to say 0.4, 0.5 hertz. And the second order motions, this is mainly due to spar surge or sway or pitch motions. They are occurring at low frequencies here. So this is representing, or sensors are capturing that response as well. But it should be noted that these accelerometers are not typically used to evaluate the second order motions, especially when the motions are less than 0.01 hertz. The accuracy of these accelerometers, depending on the sensor specification, can be low. So we don't rely on accelerometers if you want to capture very low frequencies. So in this case, more appropriate to use riser position measurements. So you can capture the second order effects, but it is not in the scope of this study. So we are only using accelerometer data. So in this slide, we look into the impact of top tension on the riser response. The figure shows TTR1 and TTR2 accelerations at 150 feet above the lower stress joint again, and TTR1 response is in red color, red line, solid line, and TTR2 is in solid blue line. The variation of top tension is also shown on this figure. So dashed lines are for TTR1 and TTR2 top tensions. So TTR, the red line, red dashed line is showing the TTR1 top tension variation, and this dash blue line is showing the TTR2 top tension variation. So when we look here, we see that the TTR1 top tension increased from 440 kips to 835 kips, somewhere in the middle of the campaign 2. And the TTR2 top tension is increased from 545 kips to 675 kips. It happened right at the very beginning of the monitoring campaign 2. So we see that TTR1 accelerations or motions reduced by a factor of 2 following the increase of top tension. So one might say that, oh, maybe it's due to environment, right? Because we are seeing this variation in the accelerations. So how do you know it is due to top tension variation? But we are monitoring TTR2 simultaneously, and so for the constant top tension, we don't see a drastic change in TTR2 motions. So it is also affected by the environment. We see the variation, but we don't see that drastic change. So it is only occurring for TTR1 right after the increase of the top tension. Okay, so we are seeing that the riser motions are drastically affected by the top tension here. So in order to assess the effect of top tension on the riser response, we look at the same data but in a different way. So in this case, we are correlating the RMS accelerations with measured wave height. So the horizontal line here shows measured wave height during the monitoring campaign, and the vertical axis shows the RMS accelerations for the riser. Again, for the sensor right above, I mean at 150 feet above the stress joint. So the red data points here represents TTR1 motions at 440 kips, while these blue dots here for TTR1 motions at 835 kips. And the green data points are also added as a reference here. It's for TTR2 at 675 kips. So we again observe that TTR1 accelerations reduced by a factor of 2 with an increase of the top tension. This is, we can see it clearly over here. And also for the same wave height, say at 8 feet, when you increase the tension, you observe less scattering in the riser motion. So for higher tension, we are seeing less scattering than those observed for the low tension setting case. Okay, so how are we going to calculate? So far we looked at we performed data screening, we looked at the statistics, we correlated to the environment, we looked at the spectral response. So we try to understand what's going on in the field and what type of motions are controlling the riser motions. Now, so how are we going to use this data to determine the fatigue accumulations or fatigue damage rates at the critical locations? So to this end, we use transfer function approach. So it's described in this sketch here. So what we do is we first derive transfer functions in frequency domain by performing finite element simulations. I'm not going to go into too much details over here how this is determined, but I can provide more data and maybe share some papers or technical documents so you can get more information on that. And we generate transfer functions, and using these transfer functions we determine, so we have the sensor data and we calculate power spectral densities for the measured accelerations coming from this sensor, and we, using the transfer functions, we obtain bending moment PST power spectral density at the fatigue hotspot. I mean, ideally you can extract the bending moment PSTs along the length of the riser using just one sensor. But of course, when you get away from or for at distance, the accuracy becomes less because of the damping. But in general, the transfer functions are used to correlate the measured accelerations at the sensor location with the bending moment PSTs at the fatigue hotspot. So once we get the bending moment PST at the fatigue hotspot, then we can calculate fatigue using a sine curve and a sine curve approach, or and using SCF values. And this method is actually applicable to both the wave and VIV events, so you don't need to worry about that. Since all your measurements are, your measured acceleration PST includes all the information related to riser wave response and VIV response, so all you need to do is just use the transfer function to get the bending moment, and this includes the stresses due to both wave and VIV. Like I said, I'm not going to go into too much details of the fatigue calculations, but what I can tell you here is just want to show some governing equations. And by means of Dirichlet's method, we calculate the bending moment histograms from bending moment PSTs. And next, we use bending moment histogram to calculate fatigue damage for given fatigue details like SN curves and SCF values. Again, if you are interested, I can share more information about how this Dirichlet method is used. Now let's take a look at the fatigue results calculated based on logger data using the transfer function approach we described in the previous slide. So here you see first TTR1 fatigue damage rate. Again, it's shown as this red line, and the top tension variation is also shown throughout the monitoring campaign with this dashed line. So, and then when we look at here, we see that the TTR1 fatigue damage rate reduces almost by a factor of 10,000 after tension increase. So this is a drastic change in the fatigue response. When we look at the TTR2, yes, we are seeing a little bit variation in the fatigue damage rate for TTR2 as well, but so it is a slight increase in the tension, and it's happening at the beginning of the campaign too, but we still see that the fatigue damage rate reduces by a factor of 10 almost here. So this is the overall results when we look at it. So as you can see, the riser fatigue is highly sensitive to top tension provided by the ARICAN. So it is important to check and evaluate the tension settings in the TTR systems. So in conclusions, what we can say is most of the TTRs are currently reaching their design lives, and there is limited industry guidance addressing their life extension programs. And riser monitoring can provide assurance for the system performance and integrity in service. Monitoring data considered in this study show that TTR fatigue can be highly sensitive to top tension provided by the ARICAN during the service life of the riser. That's why it is highly recommended to track the in-service operating tension of the risers, as it is a key input for life extension assessments if you want to do life extension assessment in future, and also if you want to evaluate the existing fatigue accumulations in the riser system. So that's all for today, and if you have any questions, you can go ahead and write on the chat. Yeah, it's with you, Victoria.
Thank you, Bulent. That's great. Thank you for all the information. We've already had a few questions, so I'll get started asking those. And if our audience has any more, just feel free to keep sending them in, and we'll ask as many as possible. Okay, first question. You said that the total duration of the monitoring campaign is 18 days. Why is that short? Why is it that short? Is it possible to conduct much longer monitoring campaigns?
So it's a good question. So we don't typically do very short monitoring campaigns. It's very specific to these ones. It's related to the objective of the monitoring campaign, because the client wanted to see how the riser response is changing due to tension variation. So it is specific to this, but if you of course want to do life extension type of monitoring campaign, you can conduct monitoring campaigns if you use standalone battery operated loggers. You can do monitoring campaigns up to 1 year, maybe even longer depending on the configuration. The thing is, here we wanted to, since we are highly interested in the riser response for tension variation, we wanted to have continuous data. But for typical life extension type of work, you can change the data logging settings, and you can use battery more efficiently, and you can collect data up to 1 year and even more for standalone battery operated systems. Yes.
Okay, perfect. Thank you. Next question is, riser VIM fatigue can be critical for spars. Did you determine riser fatigue due to VIM using
yeah,
field
like said
measurements?
in the presentation, yes, for spars, the vessel induced motions, VIMs, are important, and that is also affecting fatigue in the riser at low frequency. For this specific monitoring campaign, we did not track the riser motions due to VIM. Like I said, it's occurring at low frequency, and these accelerometers cannot be used for low frequency to capture low frequency motion. So you need to have a different set of sensors, or you should use position sensors to measure the riser response. But yes, we did other checks in the study for VIM, but it's not presented here.
Okay, thank you. Next question, what is the sensor's battery duration?
Okay, so like I said, it can up to so here in this study I showed a small sensor, and the battery life, if you do fatigue monitoring, can be close to 100 days. But if we have a different type of sensor, it has a bigger battery pack, and the battery life can be more than one year. But it is, again, it highly depends on what you collect, what data you are collecting, how many channels you are using, how many sensors you have, and also what is your logging configuration. Are you collecting data continuously, or like I said, doing this, say, 15 minutes or 30 minutes every 2 hours or 3 hours? Then that will you will have longer battery life. And yeah, so it is also acceptable if you do such intervals, especially for long-term fatigue assessment. That is acceptable.
Okay, thank you. Next question, how do you deal with mean stress issues for fatigue life prediction when both the tensile stresses are varying along the cause by weight and wave motion?
Very good question. So most of the time, so it can be included in the SN curves. So you can define your SN curve such that it can also include the mean stresses. But in this case, the sensors, they are not really giving us any tension stresses, right? Because we are using accelerometers, and we are calculating fatigue mainly due to bending stresses. You can include the tension, but to do that you need to use different type of sensors, such as maybe strain sensors. They need to be installed in the monitoring system.
Okay. Next question. Would it make sense to use this type of device on an SCR or an FLWR?
Yes, we commonly use them. We perform a lot of monitoring campaigns using on these riser systems using these sensors. We have a lot of examples, and if you are interested, I can give you more information on that. Yes, we use them a lot. Well, it depends on, well, yeah,
Perfect.
if
Yeah,
you have
and
any
maybe we
questions,
can reach
just
out.
email me and I can give you more information on that. The thing is, so of course it depends on the insulation. Um, so these are magnetically attached. But if you have insulation on the riser, then we need to use special subsea clamps, and they are also ROV deployable. You install ROV deployable clamps, and then you attach your sensors on this clamp, and we do this a lot. Yeah.
Okay, thanks. Next question. Did you calculate riser fatigue using logger data in time domain?
Um, yes, you can do that. The thing is, yes, the sensors collecting data as time traces, right? It's in time domain, and depending on the fatigue methodology, you can do fatigue calculations in time domain as well. But in this case, it is done in the frequency domain. And like I said, we used Dirichlet's method for this fatigue calculations. It is in the frequency domain, but there are also other methods. So rainflow counting can be done. Again, you are using transfer function approach, but you do rainflow counting to do the fatigue calculations. Yes. Any other questions? Oh, very good.
Okay, great. Thank you. Not a question, but someone had asked if we could provide some related literature of the methodology to relate the data acceleration with the bending
Mm-hmm.
movement for fatigue life analysis. So maybe I can get
Yeah,
with you afterwards and you can
certainly,
contact
certainly.
that guest
Yeah.
directly. Okay, perfect. And if anyone has any more questions or would like some more clarification, please reach out to Bulent. His information's right there. I think that is all the questions that we had. So I just want to say thank you to Bulent for all the information. That's all the time that we have. And if you, like I said, if you think of any more questions, you can reach out to Bulent directly. And thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening once a month. You can check out the 2H website and LinkedIn for more details and to sign up. And you can look out for the recording of the webinar in your email in the next 24 hours. And we hope you all enjoy the rest of
Thank
your
you very
day.
much for
And
joining.
thank you.